Welcome to this video. We are going to learn about properties of waves. One type of wave we've learned about is light. Light is an electromagnetic wave. It looks something like this. The arrows represent disturbances or oscillations in the electric field, shown in blue, but also in the magnetic field, shown in red. So remember, the electric field is what protons use to push against each other. And the magnetic field is what magnets use to push against each other. So these fields permeate space, and when you get oscillations in the field strength that look like this, that's an electromagnetic wave. We said that sound can be drawn using wavefronts and rays. Sound can be spherical, but we could also have sound as plane wave, which means that the compressions do not make circles, rather they make planes, two-dimensional planes. Now, these are both waves. Light is a wave, sound is a wave. I wonder if we can use the wave drawing in the case of light. Light, we know, does not have compressions like sound. Instead, it has crests. So let's consider a wave, a light wave, which has a lot more crests. I'm not showing the magnetic part in this case. I'm focusing only on the electric part. These crests are located here, 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 and so forth. Well, wait a second. If I mark where the crests are, then what I'm basically marking is a wavefront. And the ray would look something like this. So the same way that we have wavefronts and rays for our sound waves, we can draw wavefronts and rays for electromagnetic waves. And what we're going to talk about next are properties that waves exhibit. These properties are exhibited by light waves and sound waves alike. What better place to consider properties of waves but the ocean, which has lots of waves. So imagine you're out fishing, and some light strikes the ocean. The ray looks like this. Now we're going to take away this kind of wavy surface, and we're going to act like it's a horizontal surface. This light can do two things. It can be reflected off the surface, or it can be transmitted into the water. Now, when it's transmitted into the water, you might think that the light just continues on the same path. But that's not what happens. When the light enters water, the light bends. This bending is called refraction, and we'll study that in this video. Here's a summary so far. At a boundary, like between air and water, waves, like light, can be reflected, and they can also be transmitted. Sometimes they're just reflected, sometimes they're just transmitted, and most of the time, both happen. When waves enter a new medium at an angle, they can change directions. Now, why does this happen? Why does the wave change directions? It's hard to understand the link, but here's the answer. Waves travel at different speeds in different media. For example, light travels faster in air than in water. So the light slows down in the water, and that slowing causes the light to bend. Waves refract because of the change in speed. So this is a causal relationship. Now remember that I've only shown in purple the rays. Waves, light waves, consist of crests. If I wanted to mark where the crests are, I could put wavefronts into the drawing. And over here I could put wavefronts as well. And if you put wavefronts in here, look at how they appear. They're closer together. Whenever a wave slows down, the wavefronts become closer. Now, in physics, we like to measure things. We like numbers, and we like putting math in using math to describe the things that we see. So we have a value, a number that we calculate. There's this thing called index of refraction, and every medium has a value of n. That value indicates how much light slows down in the medium, and it also indicates how much light bends in that medium. The higher the index of refraction, the slower the wave travels, and the more it is bent. So, for example, glass has a pretty high index of refraction. So that means that in glass, light slows down quite a bit. It also means in glass, light bends quite a bit when it comes from air.